Good evening, everybody. Depending on where you're from, but here in South Africa, it's evening now. So good evening. My name is Phyllis Kwenda Mazingeni. I'm I'm a council member of the South African Systems Dynamics chapter, responsible for student affairs together with Dr. Young Sebastian, who will briefly say something later on. So welcome to our first seminar in 2022, where we are talking about applied systems dynamics for students and beginners. So I'm sure this is going to be very beneficial for the people who are beginning to use this methodology. Next slide, please, Dr. Botha. Next slide, please, Dr. Botha.
I can see the next slide. I think it's just taking time to load on your side, Phyllis.
Sure. Now, if you can see, it's fine. So briefly about our chapter, our mission is to encourage the growth of systems dynamics in Africa, basically. And then the vision is also to be recognized internationally as one of the leading systems dynamics chapters, particularly in Africa. So you can check our website and so that you can find out more about the chapter. And our current president is Dr. Botha, while our outgoing president is Dr. Nalini. And we have a lot of activities that the chapter conducts, but then these are some of the major ones. So we have each year we have a conference. This year it will be the 10th conference, and I don't know if Dr. Nalini you can speak briefly something on the conference.
Hi everyone, I'm Nalini. So yes, like Phyllis, so welcome firstly to everyone. It's an absolute pleasure to be able to host you guys to our very first seminar of the South African System Dynamics chapter. Hopefully you guys will be so inspired that you will join us for the remaining seminars that we have planned for the year. In terms of the System Dynamics, the South African System Dynamics Conference, this will be hosted from the 16th to the 18th of November this year. We will share the link in our message box, and we really do encourage everyone to participate, either just as an attendee or to submit a paper, which, you know, it could be a paper or a discussion, presentation, or a case study. This year, we're open to lots of different options, and our topics are actually very diverse. So we're covering, because it's our 10th and our really big anniversary for our conference, we will be having a variety of topics, from systems thinking to system dynamics to systems engineering, to data analytics, and having tracks and all of this. It's a 3-day conference this year, which is also very special to us. So we hope that you guys will register. Like I said before, we will share the link on the chat. Thank you.
Thank you, Dr. Nalini. And then our other major activity is systems dynamics competition. Dr. Botha, can you please briefly tell us something about the competition?
Sorry, I just have to get control back. So yeah, basically the competition, it will be the 5th year that we run our competition. And the purpose of the competition is to give people an opportunity to number one, learn about system dynamics. So we've got a series of workshops that starts from the very beginning, but it also then guides you through the process of developing a simulation, and in the end providing us with a report which will then be adjudicated. And this year, for the first time, what we're planning to do is to break the competition up into 3 levels. So there will be an entry level for people who are just beginning, 6 months or less of experience. There'll be one for intermediate people who've got more than 6 months and less than, let's say, 2 years. but then there'll also be an opportunity for people who are experienced in system dynamics to enter the competition. One of the big benefits of the competition is while you're busy with the competition, if you're enrolled and you achieve all the milestones, you get access to Stellar Architect. So basically the full-blown version that you can then use to prepare your simulation for the competition and for your entry. So if you're interested, again, on the website, there's a link to the competition that gives you all the details. It will also give you an indication of where to enroll and take part in that. The schedule is also posted up there. I'm not going to try and remember all the workshops. I think we've got 5 or 6 different workshops and then some intermediate milestones that we want people to achieve. Thank you, Phyllis.
Thank you, Dr. Botha. Dr. Young, can you please tell us a bit about the seminars that we have in the chapter?
Yes, thank you, Phyllis. We have actually started a seminar series this year as part of the chapter to give students who are students and professionals who are registered members of the chapter. And by the way, we have given students up to June to join the chapter for free, after which you'll be required to register, pay and register, so that you can have the full benefits of the chapter. So we have this seminar series like every 2 months. This is the first of many. We have another one in May, another one in July, and then another one in September, and then in November on different topics. At the end of this seminar, we are going to also ask you to actually tell us what you would like to learn in terms of to propose some of these seminar ideas. But we want to be as broad as possible to cover different topics of systems thinking and systems dynamics, to give people who have no background, like a little bit of background, lay a foundation for you to actually learn what systems thinking and system dynamics are all about. So we are going to be communicating with you guys, I think in the next coming months, to talk to you more about some of the activities that we have. We also have some student activities planned. We are also going to be sharing some dates and important information on some student-related activities that we have. So we look forward to having you guys here and have a session with you guys. Thank you.
Thank you so much, Dr. Young. Without wasting much of our time, I'm going to introduce our first speaker of this seminar. There's going to be 2 speakers. The first one is Dr. Nalini Suknanan-Pillay. So Dr. Nalini graduated with an engineering degree at the University of Witwatersrand in South Africa in 1994. She then worked as a production engineer in the steelmaking industry, where she dealt with line expansion and optimization projects. In 1997, she joined Eskom's research business unit, where she was involved in generation, plant-related research, as well as the development of knowledge management diagnostic programs. From 2003 to 2007, she worked privately, developing and facilitating skills enhancement courses for educators while publishing several fiction books. She rejoined Eskom in 2008 to manage generation engineering research activities. At the end of 2011, she set up the Eskom Systems Dynamics Center while completing her master's in sustainable energy engineering at the University of Cape Town. She played a major role.
Ser flexible, como dice Andrés, que la comisión es la que decide sobre los temas, pero que tiene, yo les he mandado a la reglamentación, enfocados en...
Can you please just mute your microphones, please? If you're not presenting, please.
Regreso de la carrera. Entonces, con esa...
Phyllis, you muted?
Yes, I actually muted everybody. Phyllis, you can unmute yourself and speak, please.
Sure. Thank you, Dr. Young. At the end of 2011, she set up the ESCOM Systems Dynamics Center while completing her master's degree in sustainable energy engineering at the University of Cape Town. She played a key role as chief mentor in the ESCOM Research Business Unit to establish a comprehensive process to fast-track and promote personal and technical growth of graduates in training. In 2018, she assumed the executive role of ESCOM Corporate Specialist in Systems Dynamics and completed a PhD in Industrial Engineering with contributions to the field of systems engineering at Stellenbosch University. She is a founding member of the South African Systems Dynamics chapter and held the post of president for several years. Together with the ESCOM Systems Dynamics team, she started the very first Systems Dynamics conference in South Africa and Africa in 2013. Dr. Nalini lectures ad hoc in applied systems dynamics at various universities and has authored and co-authored several internationally recognized papers using a systems dynamics modeling approach. Dr. Nalini gets her inspiration and passion for life from her three children, Tejal, Anita, and Nikhil. Over to you, Dr. Nalini.
Thanks, Phyllis. I now understand why you asked about the long CV. We should have given you the shortened version. That was actually from the book that we actually published. So that was the long story that people could read at the end of the System Dynamics book. But thank you for that. And again, welcome to everyone who's decided to join us for our very first System Dynamics seminar hosted by the South African System Dynamics chapter. And of course, you would have met our hosts. That's Dr. Young, Sebastian Yam, as well as Phyllis Kwenda. So what I'll do is I'll project my presentation. Here we go. And then we can get right into it. View full screen mode. Can I get confirmation that everything's clear and I'm audible?
Yes, it's clear and you're audible from my side.
All right. Okay, that's great. So like Phyllis said earlier, I am Nalini. I do work full-time at ESCOM in the Research, Testing and Development Business Unit. ESCOM, for those of you who haven't heard of ESCOM, it's an electricity utility based in South Africa that supplies a large part of the overall generation to the country nationally, as well as to some parts of Africa. In today's presentation, I'll just take you through a brief introduction, followed by some very basic definitions, and this may seem very unnecessary, but in my experience, I think it's really important always to start with first principles and founding terminologies. So we'll look at the difference between a system dynamics, as well as systems thinking. Then we'll get into the system dynamics method that we actually follow at ESCOM and that we propose to be followed by beginner system dynamicists. So you don't end up in a situation where you start modeling and through the process you end up in such a complex model that you can't actually see the end of it. So the process that we follow, as well as the detail behind that, you'll also find in the System Dynamics book. We'll send through more details of the book in the chat. I'll then, depending on whether we have enough time, take you through the model demos and then we can conclude. So here, I just want to run a poll and I want to ask you in your current capacity, what would you say you are? I mean, do you think you're a pilot in terms of the perception that you have of pilots, or do you think that you're an aircraft designer, or do you think you're both? Now, I think Young will run the poll, but I'll give you about 10 seconds if everyone can actually then respond to this in the chat or on the poll. Okay, Young, are you running the poll?
Yes, the poll is running.
Okay, great stuff. So the reason why I actually asked this question, and it's, you know, it seems like a very odd question, but let's look at things in terms of what pilots do in the aircraft industry. Now, your pilot is somebody that keeps the plane in the air. Your aircraft designer in the aircraft industry is someone who makes sure that the design of the aircraft provides enough stability under your extreme conditions. And the learning tools that these guys use include flight simulators. Now, when we look at organizations, our pilots are those guys that make key operational decisions that are generally reactive. And in the case of Eskom at the moment, we are very much in the pilot, keep the plane in the air mode. In terms of your aircraft designers in an organizational context, these guys would design the organizational policies and develop strategies that would influence decisions. And some of the tools used in this would be your management flight simulators. So now I can't see your results, but you in your personal context and capacity, I think if you in pilot mode, you probably have to re-strategize. And if you're just strategizing and not introducing some of the forward movement and trying to keep up with your pilot activities, I think you might also want to relook at your approach. Generally, there should be a balance between the roles in terms of your approach to the way you see things. And our management flight simulators, our system dynamics models are some of the tools that we use to try and help us do this. Now, like I said before, the definitions for systems thinking, and system dynamics, it's important to understand this because in a lot of cases, and I don't know if you guys have actually seen this, but I have come across it several times, and our system dynamics team as well in Eskom. And people use systems thinking and system dynamics very interchangeably. And this shouldn't be the case because you should understand these fundamental concepts upfront. If we look at a system, and this is thanks to J.O. Arantes, his cartoon, I absolutely love these cartoons. But if you look at the definition of a system is an arrangement of parts, right? Parts or elements which interact, they come together to achieve a particular function. Now, a system has many characteristics, but a system may also change in terms of the structure and behavior over time. In this case, there's a little system here that peed a lot every hour. The little system became a bigger system, older system, and now pees in Morse code every minute. In terms of systems thinking, the iceberg model is something that we use quite often to try and get across this concept. You'll find that I start the iceberg model with a mental model, and I end it with a mental model in terms of what lies underneath the underlying structure. And this is because we all have mental models at every stage. So these mental models are usually formed subconsciously based on what we perceive to be the situation and the cause of a particular event. And generally, it's based on our intuition. In terms of events, the events are the very obvious, visible, apparent occurrences. Now, these events, we can compare these to things like your newspaper headlines, for example. Now, when event level observations are made, what's our tendency? Our tendency is to react immediately. And so what happens when we react immediately? We start treating the system problem symptomatically. We're providing end-of-pipe solutions. So after a while, when we actually observe these events, we understand that there's a particular pattern that actually starts emerging. This pattern of behavior is what characterizes the nature of the system problem. Now, these patterns are based on what we expect is most likely occurring and resulting in the event. And when we start seeing these patterns, yes, we are a bit closer to trying to understand the cause of the problem, but we require further analysis in order to get to the underlying structure and to understand the root cause of the problem. And so this is where systems thinking comes in, where we employ all of these tools, we use all of these tools, develop these tools to try and help us then understand the base or the underlying structure of the iceberg model. Only then can we design solutions and identify leverage points that will help us to get fundamental solutions as opposed to symptomatic treatment of your system problem. Here we have the definition of system dynamics, and the important things to actually remember in this definition is that system dynamics is a computer simulation method. It allows decoding of the complex system problems. How? By incorporating two very important things, which is your feedback loops and time delays, which are linked to the system structures, so that the behavior of these system problems over time can be identified through plausible scenarios. And these then result in emergent yet counterintuitive outcomes. Now, if we look at our prof over here, what do we find? With prof, he's showing us a bit of a very simple feedback loop. So he's very stressed out. He's got like all of these students at his door, and he's like really stressing to try and get his papers published and his lectures sorted out. And so he decides, okay, you know, I need a smoke. He then starts with a certain number of cigarettes. There's a release of dopamine in the brain. He feels wonderful. Oh, love it, love it, love it. It's helping, right? But then what happens in the long term? What our prof actually then realizes is that, hold on, having this many cigarettes and this frequently has resulted in a nicotine addiction. And this is a completely unintended consequence of him trying to get to addressing a problem without getting to the fundamental root cause of it. So in terms of the method that we are all very familiar with in terms of system dynamics, if you're a system dynamics modeler, you would have come across some of these methods that cover things such as, firstly, your problem identification, trying to conceptualize the problem, articulate the problem, identify key variables, patterns of behavior, defining and developing your causal loop diagrams. Secondly, there's another aspect to the method that some people may be familiar with, and that is formulating the model. The third one is actually testing the model and further development if required. And then, of course, we get to the heart of why we're actually using system dynamics modeling. It is, of course, the perfect tool to test different policies, to do your sensitivity analysis and your scenario analysis, to try and understand the impact of your policy decisions. Now, in terms of the 8-step modeling process, which we actually follow very, very judiciously, very rigorously, we have, firstly, the project idea. So we have this project initiated, and then we go to concept to context. We then go to a boundary setting. We go to a system analysis, followed by model development and design, validation and policy insights, model handover, and model maintenance and updates. And these two are very, very important, yet missed quite frequently in literature, this is what actually allows you to have an extended shelf life in terms of your system dynamics model. I'll go through each of these then in detail, which is my part of the presentation. So like I said, in this step, your project is initiated. Now your project can be initiated, and I talk from an industry application point of view, not an academic point of view. We have built several models for our company, and a lot of them are either operational or strategic. And all of these, in terms of the method and how we actually approach it, is based on actual experience. So the system dynamicist can either initiate the project, or a customer approaches us and initiates the project. What we realized is that in these projects, especially if you're in an industrial environment, you have to look for an executive sponsor, because the executive sponsor is the guy who will help you to actually give you the right level of airtime with your EXCO members and be able to support you in terms of implementing the model. Here, what we also found works is once you develop the model, you must make sure that at the beginning, you know, there's a technical owner, there's the guy that will run the model, generate the results, send it through to the necessary levels, whether they're management levels or other technical levels, to make sure that these results are then implemented. So you'll find what I have here is a very simple graph. On my y-axis, I said, what would variable y be? What should variable x be? Now, asking people, what are we solving for? And what should this graphical result or output look like? It doesn't mean that we're prescribing this preconceived result in terms of an emergent model solution, because the trend may be non-intuitive, it may be unexpected, but it may also then reflect the system variables which may have to be reported on. We just find it's a very, very simple yet effective tool to actually use in engaging with our stakeholders. There are also other very important things to remember when it comes to this step. And that is when you engage with your customers, you emphasize certain things. You emphasize firstly that the model is not a crystal ball. You cannot press a button and the model will predict a future in terms of whatever the system problem is that you've modeled. The second thing is that the model cannot think. It can't think for the user, and it will not output an exact answer with the click of a button without you actually discussing it and having that strategic dialogue around the scenarios that you will run with the model. The third thing is that the structure can't be altered to provide bias for a predetermined result or an output. So you can't say, hold on, let me actually just develop this model to prove a theory that I have, or to justify a certain decision for getting money approved for a project to happen. So you can't actually then do that. And then we also emphasize the difference between modeling a system and modeling a system problem. Because if you model a system, you're modeling a piece of string. Quite honestly, you are modeling a piece of string. There's no definite boundaries, and you could go on forever. But if you're modeling a particular system problem, you can identify your system boundary and your variables. In terms of the second step, we call this concept to context. So now you start contextualizing this problem that you've identified and the system problem that you're trying to then model for. Part of this step actually includes some very important things. So in order for the customer to contextualize the project requirements, they would have to ask some, or we ask them some guiding questions. And some of those include the relevance of the time horizon to the problem at hand. Is this time horizon relevant? You know, do you want to model 1.3 units in time, or do you want to model 15 units in time? Which one is more relevant? This is exactly the same thing that's been modeled. But because I said I want to look at 1.3 units in time and see what my result is, I have a very different understanding and perception of what the result is. But if I choose my time period very carefully, I will find that I see a very different picture and a very different result, and my interpretation of the system behavior over time is very different. So you need to choose your time horizon very carefully. The second thing is your data availability. And generally you look at basically what historical data do we have, is it relevant, and so on. Those are the type of questions you would ask. And of course, you know, just your modeling timeframes are also very important. So in terms of the third step, this we call collaborative brainstorming, ideation, and boundary setting. In this step, we have a very popular causal loop diagram. A lot of people may be familiar with causal loop diagrams, but if you're not, a causal loop diagram just quite simply is constructed through generally group model building, which is a facilitated modeling method where you have a whole bunch of stakeholders and they're guided through a brainstorming session to determine as many variables and relationships between these variables that's linked to that system problem. Then you have what we use in terms of our modeling steps, and this we call a system architecture map. System architecture map is very different to a causal loop diagram. With the system architecture map, you're actually looking at your upstream and downstream variables. You're looking at all of those driving forces and externalities that are affecting the environment, the specifics that you're going to be modeling. Then we have something else which is more important, and I really have to stress that this is far more important than jumping into the software and to start modeling. You have to understand in terms of your system analysis, interrogate the data, understand the data, do some work in Excel beforehand. Your analysis could include things like your statistical methods, or you can even use programmable codes, which we've done, to determine any patterns, any relationships, you know, to try and order and simplify both your qualitative and quantitative data into a time resolution that will be suitable for importing into your system dynamics model. Sometimes, you know, your empirical data may have gaps. You can even use classical regression. You can do time series decomposition. You can do least squares approximation. Anything in terms of understanding and analyzing your system beforehand. In this process, it's very important. There's one thing which is like critical, and that is that we dismiss our perpetual linear growth trends. And the premise is that real system elements, they have biophysical constraints. And if your appropriate time frame has been selected, these trends will show that system variables do plateau, and they will reflect the carrying capacity of the system. Then in terms of model development, here, of course, we establish what our modules and sub-modules will be. We specify our decision rules, our parameters, our behavioral relationships, our initial conditions. We also do tests to make sure that it's consistency with the purpose and the boundary of our problem or a system problem that we're modeling. Yeah, so that's it. I see I'm running out of time, so I'm going at a speed. And this then is just an example of one of the interfaces we have, I have developed using IC Stellar Architect. I just want to quickly actually do something. So I want to show you one of the models very quickly. Guys, do we have time for that? Where we've applied the method and then we get to the model. So I'm just going to try and open this up very quickly. And of course, you know, when you're in a hurry, nothing is quick. So let me just wait for this. Okay. Okay, here we go. I'll just open the last simulator I'm working on. And this simulator, I'll just show you then the kind of complexity you can end up with in terms of all of these feedback loops and stocks and flows and all of that. And then in terms of this particular software, we build these engagement interfaces, which really help us a lot in terms of engaging with the customers. And we find that we can run scenarios, engage with different groups of people. Here, this is looking at setting electric vehicle targets. For example, let's put in what we perceive to be a fairly low target for South Africa. We'll put in a 10% replacement of our fuel cell electric vehicles, 10% of our hybrids, and 10% plug-in hybrids.
Are we supposed to be seeing the stuff on the screen?
Yes.
No, we are seeing you.
Oh man, sorry about that. Oh, you should have told me a while back. I was like showing off with my with my model structure, and I was like really getting carried away here. Let me just show you my model structure again. So this is what I was trying to show you in terms of the monsters we create. You know, this is basically some of the models that we create. It goes on and on and on and on. So that's generally where you can end up. And this is one of the interfaces. I was putting in some values here in terms of replacing our internal combustion engine vehicle population, run the model, and we can figure out how many EVs we'll have in the system, how much of electricity consumption this would mean, what our decrease in terms of our transport emissions will be. It looks like a serious dip, but my scale is very small here. And then we can change things like the age of the vehicle, run it, and then after a certain age, it will scrap a certain percentage. We can then split these into different provinces. We can work out then what our targets will be depending on our ratios for our charging stations per 10 EVs. And we can do a whole lot of different scenario analysis. And I'm going to stop there because I need to give Andries an opportunity. So that's it in terms of where we end up with applying a system dynamics methodology. Thanks, everyone.
Thank you very much, Dr. Nalini. That was a brilliant presentation right there. Okay, Phyllis, you can go.
Thank you so much, Dr. Nalini. I did not see any questions for you in the chat. I don't know if there's anyone who has like a quick question for Dr. Nalini.
Has his hand up.
Thank you, Dr. Nalini. Yeah, I think it was a great presentation. And I see the model is quite complex. So my question is, how do you explain, or how do you take people through such a complex model in a way that people will understand the idea behind it? Thank you.
So basically, there's different levels in terms of trying to take people through the model. So sometimes if, for example, and this is going to happen quite soon, where we are going to present the model to EXCO and board in Eskom, there we would just take them through one engagement interface and say, these are the different scenarios we can run in terms of electrifying our fleet, which is an option that Eskom is looking for. And if we change import duties, this is what the impact will be on a total cost of ownership and our repayments. And we do different scenarios in terms of that. Now, if we're working with other groups of modelers and other people that are also looking at EV projections and fleet electrification, we would have a longer session where we would actually take people through far more of the model. And we would explain, run the scenarios, and have that technical discussion around it. So it's not only about showing and telling about the model, but also about running the scenarios, looking at the results and having that engagement, which is also what we do through the process. If it's with our customer, we actually have applied system dynamics courses run in Eskom, where they get an introduction to how the modeling actually takes place. And then that's followed by them understanding and being able to follow in terms of the development of the model and when we run the scenarios and how exactly the stocks and flows work and things like that. So there's different levels of presentation and explanations. Okay, I hope that's it. I don't know if there's nothing else. I think Phyllis and Jon can probably introduce Andres.
Sure. Thank you so much, Dr. Nalini.